Hello, everyone. In this video, we are going to talk about the DC to DC converter, more specifically the buck boost and buck boost converters. Okay, these converters would allow us to change the level of the voltage in the output in respect to input. For example, the buck converter would step down the voltage. So whatever voltage we have in the input, we are going to have lower value, lower level of the voltage at the output. Boost would work the other way. So whatever voltage we have in input, output would be more than input. So we are going to boost the voltage, step up the voltage. And the buck boost circuit would basically deliver us a mixture of these two performances. Okay, now let's talk about it in a more detailed way. Let's look at the buck converter first. In the buck converter, we have a switch, we have a diode, an inductor, a capacitor, and obviously a load that we are supposed to supply. Okay, now, when the switch is on, when the switch is closed, the energy from the source would move toward our circuit. Okay, now, both inductor and capacitor, as you know, are energy storage component. So they have the ability to store energy in them. So now, look at the circuit. When the switch is closed, the current going toward the circuit, okay, meaning the current passing through the inductor, and you know that the inductor doesn't like changing the current, so it is going to first resist against the increase of the current, but when it's magnetized, meaning there is an energy stored in it, okay, it would keep the value, okay, and if for any reason you cut the current, again, it would use that stored energy, okay, as an inertia, so it would not let the current to drop to zero instantly, okay. Now, when the switch is on, we have a injection of the current, meaning we are going to have energy stored in L, and also we are going to transfer charges to the capacitor. That means we are going to also charging the capacitor and providing some current for the load. Okay, now the trick of the buck boost happen when we are opening the switch. So if the switch is off, okay, then you don't have any supply, okay, but this diode, which was reversed bias in the on time of the switch, in the close time of the switch, now became forward bias based on the KVL. You can run the KVL and find out that. Therefore, the energy of the inductor would also again transfer that ramp down of the current in the inductor would transfer to the capacitor. So there is going to be a circulation of the current here. With that type of performance or characteristics, okay, it means that we can control the energy stored in a capacitor, which basically give us the voltage across the capacitor, would determine the voltage across the capacitor. Now, how we can control the level of the voltage across the capacitor? Very simple. By tuning the time of on time and off time of this switch. So as much as we decrease the on time, that means we have less energy stored in these two components. That means we have lower voltage across it. Okay, now the boost converter, okay, works kind of similar to that, okay, but in different manner. Now, the switch would short circuit the terminal, one of the terminals of inductor to the ground. So what's happening here is that when the switch is off, we have the current passing through the L passing through the diode, charging the capacitor, and also providing some current for the load. Now, when the switch is on, now the diode is reverse biased. That means no current here, and the L is short circuited. So we are going to have a rush of energy or current into the L. So beside the nominal current of the source, we are going to have more energy is stored in the L. And after a while, when we again open the switch, that extra energy, okay, would move toward the capacitor on top of regular energy that we supply from the source direct. That means here we would have a step up. We are going to step up the amount of energy that we are transferring to the capacitor, meaning we are going to step up or boost the voltage across the capacitor. Okay, now the buck boost controller is basically the series connection of these two circuits. Forget about the sources, okay? The rest of the circuit and the loads, the rest of the circuit, which is actually the circuit for buck and boost, okay? If you put them in series, you can see that like this circuit is the buck circuit, okay? You can see that up to here, up the middle of this inductor actually, okay? Is the buck circuit, and then if you connect these in series with that, okay, it is going to be the boost circuit. Now you have two L. This L here is basically, they are going to be in series, so they're basically the summation of the two. Okay, so this is what's happening in the buck boost kind of like converter. Okay, now the buck boost converter, the principle of working with a buck boost converter is if this switch is always on and you control the duty ratio or on time, off time of the second switch, okay, you are going to have, as you can see here, you are going to have a boost situation. Okay, you can see that. If this switch is on, basically our circuit becomes the boost circuit. Now, if this switch is tuned by the duty ratio, you are controlling this switch and keep the S2 open, all the time. Now you would have, as you can see, you would have a buck converter. So by closing the S1 and changing the duty ratio of S2, you control the level of the voltage at the output and you could boost it. And if you open the S2 all the time and then tune the on time, off time of S1 with like a PWM, then you would have a buck performance and you can step down the voltage of the output. Okay, now these type of converters, since they work with the L and they count on the resistance of the inductor against increase and decrease of the current, which basically means inertia in our system, and that inertia is what we use for like the extra energy here or draining the energy of the capacitor here. Okay, the situation, the mode of working with these two circuits would change based on the amount and the behavior of the current that pass through this conductor. What I mean, we are going to have two modes of working when we talk about the current of the inductor. One mode is that we tune the circuit and we design the circuit in a way that the current of the inductor, okay, through the time would never become zero. So there is going to be a ripple, but there always, like there is going to be on time, so it increase, and there's going to be off time, so it decrease, but it would never reach the zero line. So we tune this circuit, we design this circuit in a way that we always have average current which do not ripples to the zero or passes even the zero line. Okay, now another condition is that we design this, but the current in an off time and on time would reach the zero. So it starts from the zero, and then when it goes back before the next on time, it would completely discharge, so it becomes zero. Now, the first one, we call it continuous current mode, and the second one, we call it discontinuous current mode. Now, you can see that when the switch is on, we increase the current, and current would increase, and it's kind of like a ramp up. It's not exactly a ramp, but we are approximating, okay? It ramp up in the inductor, okay? And when it's off, it will ramp down. But the design is in such a way that we never reach the zero line. That makes the average current, the output current, to be a non-zero value, okay? And the ripples of the current, the delta I of our current, never reaches the zero. So it is gonna be a slight ripple, and the peak of these delta I, which is I peak of the ripple, would never reach the value of the average output, because if it reached the value, that means this peak is getting to zero. Okay, now this is going to be continuous mode. And now, in the discontinuous current mode, okay, we design the circuit, we apply the voltage in on time to the inductor, and as you can see, we increase the current. The current here, this is the current. The current would increase, okay, and when we switch off, it would decrease, but the level of the current here, okay, is low enough that during the off time, the inductor can completely discharge. So we are going to have a period of having a zero current during the off time. So this is discontinuous current. We still have an average, a positive value of average current in our output, okay? But the value of the ripples get more or equal to that average current. So here we have our I output, okay? And the peak value of the ripples, which is this value here from the average all the way to the peak, okay, is gonna exceed the output current. That means the negative half cycle of the ripple would cross the zero line, okay, or get zero. Now, remember, we are talking about the DC, so our load is always resistant. We don't have current, we don't have capacitor behavior or inductive behavior in our load when we talk about the DC, with the assumption that we consider the voltage output as this DC output. So these ripples would still create some effect on the inductor and capacitor at the output and the load, okay? But since we're considering that this is a DC-DC converter, so we forget about the ripples, or we design the ripples low enough that we could neglect them, okay? Then always the load is gonna be resistant. So here, we never gonna cross the zero line, okay? We don't have an alternation. Now, let's talk about how we can basically define the characteristics of the output and of the buck and boost converter, okay? And actually, same goes for the buck boost converter. We're going to talk about it later on, and how we can basically define the important variable in our system. Now, you can see that we have a switch and we have a diode, but they are not basically the component that we have to find a specific value for. They have a characteristics of like a voltage tolerance or the current tolerance, okay? Or like for the switches, the switching frequency that it could provide, okay? The bandwidth of the switch basically. Now, these characteristics, okay, could be easily defined based on what we want out of this buck or boost converter. So, for example, if we want to apply like a 12 volt, that means this one should be able to like tolerate a reverse voltage of 12 volt. So the breakdown voltage should be higher than 12 volt. Okay, and for the switching, for the voltage control, and for the gate, actually, we are going to talk about this is switch. So we are going to trigger that using either like is a MOSFET, PMOS or NMOS. There is going to be a gate source voltage that triggers this switch on and off. Okay, and that voltage gate source are going to be based on the characteristics of the switch that can conduct enough current or the output current that we want. Okay, so this is basically, these two are basically you choose the models based on the input voltage, the current that you want to like conduct, okay, and how fast you want to switch. These are basically chosen models, but L and C are the one that you have to actually calculate the value and find, okay, how many Henry of inductor you want, or how much farad of the capacitor you want. Okay, now let's move on. Now, in the buck boost, as you can see from the circuit, okay, the output voltage, the ratio of the output voltage and input voltage would be equal or closely equal to the duty ratio. What is the duty ratio? Duty ratio is the amount of time, okay, is the basically the ratio of the on time versus the whole cycle. So the time that the switch is on divided by the whole cycle is the ratio of on time, which we call it duty ratio. Okay, now in buck converter, the ratio of the output versus input, which is basically what we want out of a DC-DC converter, is going to be equal to this D, the ratio of the on time versus the whole period. Now, if you want to have a proper L, okay, so you would remain in continuous mode, which is what we want, because this gives us a proper stability for the output current. We don't ripple too much. Here, we have an average, but we ripple too much, okay? So we wanted to stay in a stable, more stable situation, so we are gonna design the system to remain in a continuous current mode. Now, if we want to have a specific level of the ripples, so we would stay in a continuous current mode, and that would also affect the ripples of the voltage. We're going to talk about it in the next equation. We have to design the L so we could actually deliver that ripples of the targeted ripples of the current. Now, the formula that you can use is to the voltage across the L, okay? The voltage across the L, you can see that this is output, this is input. So the voltage across the L times the duty ratio, okay, which give you the basically average on voltage, okay, the average on voltage over the L, divided by whatever delta I you want. Now, I want you to pay attention. This delta I is not IP real, is peak to peak. So this is mean max, this is peak to peak. This is delta I. This is IP. This is half of delta I, the value of here. Okay, this is half of delta I. Okay, so what is delta? What is this value? This value is I peak minus I out. This value is peak to peak of a current, okay, and ripples. Now, we target one based on our desired performance. So L is going to be the voltage across it times D divided by the targeted ripples in a current times switching frequency. So knowing that, we can decide there. Now, for the switching frequency, normally the buck boost converter works in like a higher than 100k hertz, okay, 100 kilohertz. But granted, what we have in the lab, the BS170 and the IRF 520 and 9530, okay, those MOSFET that we have in the lab, their level of the frequency is lower. So, like for example, BS170, if you use that, the frequency that you have to use in order to switch to work properly, because it cannot tolerate high frequency switching, is around like 5 kilohertz. So it's way less than the normal kind of like design for the buck or boost situation, but this is what we have. So we have to deal with it. Now, with this equation, you can find the L and for the buck. And with this, and then we need to calculate for the output capacitor, which output capacitor should be equal or bigger than the ripples of the current divided by 8 times of the switching frequency times whatever voltage ripple that we want in our performance. These two, these delta I and delta V, are set by design. So you decide about that. And based on that, you choose the capacitor that could deliver such a delta V. And the L would deliver such a delta I. Okay, now for the boost, because this switch basically short circuit the current is in parallel, okay, that means the output input ratio basically our boost controller is going to be 1 minus D. Okay? This is still the ratio, okay, duty ratio. So output versus input is going to be equal or approximately equal to 1 minus D. Okay, this is 1 minus D. You can consider that. You know that, okay? So actually, this is T minus D, and then divided by T is going to be 1 minus D. Let me make sure you don't confuse that. Now, for that circuit, the L that we want to design could be defined based on, again, the voltage across the inductor, which you can see this is going to be the input because this is short circuit, okay, during the 1 minus D. During the D time, okay, so it's going to be input voltage times D, okay, so it's going to be average voltage across the L, divided by our targeted delta I times frequency, okay, switching frequency. And the output capacitor, which would define whatever delta V we are going to get, is going to be the average current at the output times D divided by the switching frequency times the voltage ripple, the delta V that we want. So this way, we can calculate the values of these L and capacitor. Now, these are for buck and boost. What about buck boost? For buck boost, you need to design both L and C with both different situation of buck and boost. So first, you consider the system works as a buck, then you calculate the L and C, okay, and then you consider that as a boost, and again calculate L and C. Whichever is bigger would be what you use here. So if, like for example, here you get 1 millihenry, and here we get 1.2 millihenry, you have to choose the bigger one, 1.2. Same goes for the capacitor. Okay, so this is basically the base of how we can design or basically the theoretical background of buck boost and buck boost converter. Now, next, we are going to actually use the lab assignment 6 criteria that we defined in order to actually find the L and C and find out, okay, what is the exact circuit that we need. In our lab assignment, what we targeted as a performance of buck boost converter is defined as, in a buck mode, we want to change 12 volt to 5. In a boost mode, we want to change the 12 volt to the 18 volt. The delta V that we accept at the output for both system is 25 millivolt. The delta I for both mode is 0.3 times the output current, so 30% variation over the output current, around the output current basically. And the output current that we targeted is 0.15 amp. Now, based on these given data, we have to design the L and the C. Now, we already said the diodes basically would be defined based on the voltage stress and the current stress that we want to get out of them. Okay. And the switch would be basically based on the frequency that you want, the voltage gate source that you can supply, and the current that they should have, the capacity of the current that they should have pass. They should pass through the on time. Okay. Now, we are limited, as I said, we are limited with the diode and the MOSFET. So we are going to use the diode that we have, which all of them would provide the same tolerance for the voltage and current that we want, because we are working in a relatively low voltage and low current. The switch has another kind of limitation that I barely mentioned that in earlier, and it's the switching frequency, how fast you can turn it on and off. For BS170, okay, it's about 5 kilohertz. So the 5 kilohertz will give you a proper performance using the BS170, okay, for both of them actually. Okay, now let's move on and calculate the L and C that we need. For the buck mode, okay, we need to calculate first the duty ratio, which is the ratio of the output versus input. We know what we want, so the duty ratio is going to be output, which is 5 volt over 12 volt input, okay, which if you calculate that, you're going to have a duty ratio of 0.417. You can ignore the 7 one. Okay, so it's 41% duty ratio. Now that we have the duty ratio, we can calculate the L. So our L should be the input minus output voltage, which is 12 minus 5 times the duty ratio, which is 0.41. I'm gonna ignore the 7. Let me actually erase that. And the denominator is the delta I that I wanted to have, which is 0.3 times that 0.15, which if you calculate that is going to be 0.045 times the frequency that we have, which is 5 kilohertz. Now, if you do the math, you are going to find out that this approximately you need something else 13 milliamp. Now, how about the C of output, the capacitor in the output? For the capacitor in the output, again, we need the delta I at the denominator, which is that 0.045. Okay. In the denominator, we have 8 times switching frequency times the delta V that we want, which is 25 millivolt or 0.025. Okay, now calculating that would give you an estimation of around like 45 microfarad. So this is the design that we need for our buck converter, for the buck mode of our converter, to get the targeted values. What about the boost? Let me calculate the boost 2. I am gonna erase this part. Now, for the boost, I know that the ratio of the output versus input, okay, which is 18/12, is gonna be 1 minus T. That means if you do the calculation, the duty ratio is gonna be 0.33. Okay, now for the L, we have the formula which is V in, or V in is 12, times that duty ratio, which is 0.33, divided by that delta I that we want, which we already calculated that 0.044 0.045 times the switching frequency, which is 5K. And if you calculate that, you are going to end up in 8 millihertz. Okay, now what about the C out for our boost? Again, the formula says that we have I out, which we define as, remember, this is I out, not delta I. 0.15 times the duty ratio, which was 0.33. Our frequency is 5K times the delta V that we targeted is 25 milli, so 0.025. And if you do the calculation, you would end up in 0.4 millifarad, which is basically 400 microfarad. These are the same. Okay, now we said that in order to satisfy both conditions, we need to go for the higher value. It not include the duty ratio. Duty ratio should be the same. Okay, I'm going to talk about that in a moment. So for the L, this is 13 millihenry, and this one is 8. So this is the higher value. So we are going to go with the 13 millihenry. Now, you don't have that in the lab, so it's not calibrated number. What you have is 12, so we are going to go with the 12 millihenry. Okay, now for the capacitor in the buck mode, you have 45 microfarad. In a boost, you have 400 microfarad. This is the bigger one. Okay, so we are going to go with the 400. Again, it's not calibrated. What you have in the lab is 470 microfarad. Okay, now what we work, how we work with the circuit. When you want to do the buck moves, you are going to input the L and C based on what we designed. And then when you have those, and you put the BS170 here, BS170 here, and the diode that you have, you can use the Schottky diode. That's the better option. Or if you can't find it in the lab, which I doubt that we have Schottky diode, you can use the general diode. It will still work. Okay, now for the buck mode, as we said, you need to turn off this switch. So this one should be turned off, meaning the gate should be always 0. How we can do that? By grounding the gate. The source is going to be grounded already. Let me actually draw the BS170 here. This is going to be BS170, the drain, source, and gate. Okay. Now, if you ground the gate, since the source is also ground, this one would be this switch would not turn on. Okay. So what you are going to end up is to have a buck mode, and then you can set this one, okay, and ignite it with the PWM signal. You can create your own PWM. You already know that how you can use 555 timer to create the PWM, or you can use the signal generator for now in the lab, okay, to trigger this one. And the duty ratio of that PWM should be 0.41, so you can get the 5 volt output. Now, granted, the L that you have is not going to be the same L. The C that you have is not going to be the same C, okay? Because, and the characteristics of the diodes are not exactly ideal, same as the BS170, okay? So what you're going to end up is that this 41% would not give you exactly 5 volts, so you have to a little bit try and error and play with it to, if you want to get exactly 5 volts, okay? Now, for the boost mode, what you're going to do, let me actually replace this one also with the switch. Now, for the boost one, you need to close this one, meaning the gate should be always a positive value. How you can do that? You simply can connect this one to the positive value. So gate source should be connected to a DC value. You can also use the input voltage. It will still work. Okay, so this one will always be turned on. Okay, and then you have to trigger the second switch. This is switch 1. This is switch 2. You have to trigger the second switch by the duty ratio of 0.33. Again, this is for ideal case. You need to play with it. There's a little bit variation on that. Okay, in the real kind of like circuit. That way, you are going to have the 5 volt in a buck mode and 18 volt in a boost. Okay, now there is a trick when you want to like actually apply the voltage to the gate, and in order to actually stabilize that voltage, you need to have a bias circuit. My suggestion is when you want to apply, like this is PWM, right? This is the PWM signal, okay, connected through a resistor to the gate, okay. This way, like I use 10 ohm, doesn't matter, low resistor, okay. So you basically stabilize the current and voltage. Now, you want to bias it. So not only you want to have like a high value, you want to actually pull it down when you want to like have an off value. So you are gonna connect another resistor to the ground. Okay, so this resistor connect between the gate and ground. Now this one, since you want to have a voltage in on time, okay, this should be a very high value. I used 100K. So what I used is 100K for both of the switches. Okay, so this way you have a bias, a better bias of your switches. Now, BS170, okay, normally needs the voltage gate. This voltage gate should be between like 10 volt to 12 volt. Okay. Okay, 10 volt to 12 volt. So it would be triggered properly. This is VGS, okay, VGS, remember. Okay, now, there might be a little bit of variation because your signal generator has a limitation, so you have to kind of like work with it and find out if it works or not. Now, in the end of the video, I am gonna I'm gonna explain that in detail if it works or not for BS170. This is BS170. Okay. Now, in the buck mode, you would not have a problem. Your signal generator in the lab would not provide you 10 volt. It is going to be less than that. Okay. But in the buck mode, since you want to decrease the voltage and you have a relatively low current, you are not having a trouble. If you remember, in the IV characteristic, we have several kind of like signal, and each curve, each curve was represented by a VGS, and here we increasing the VGS, we increasing the capacity of current that we have, meaning we increasing the power that we can deliver. Okay, so in buck-boost, since the voltage is low, we don't have any much of a problem if we don't get to the 10 volt. So we are remaining in like a low region, but still we can supply. But in the boost mode, okay, when you want 18, you have to go to the higher region, and you can't based on the signal generator. I explained that in the end of the video. So in simulation, you can do that. It would perfectly work. Okay, but in reality, for the boost mode, you cannot use the VGS. You cannot supply the VGS using the signal generator because of the limitation. So the option is to either change the BS170, which we don't have, to be honest. Okay, and or you can create your own PWM circuit using the 555 timer and basically boost the signal. Now, this is basically how you can design a buck-boost circuit. We are going to move toward the simulation. We are going to simulate this circuit that we designed based on these data and see how it works. And then we are going to try to do the test using the actual component on a breadboard in the lab.
Okay, here as you can see for the boost part, since we have to have the first switch, that Q1, always running, so what I did is simply remove that and replace it with a wire. You can set the gate and source voltage in a way that basically you can set the switch in a way that it's always on. So doesn't matter. I just wanted to like simulate, so I have it this way. And the second one is basically getting a PWM signal in the gate. Okay, now I want an 18 volt at my output. So let me put the voltmeter at the output so I can see what's going to happen. The 12 volt, everything is based on the design that we talked about. So let's start the simulation. And okay, as you can see, right now I have 17.9 volt, which is very close to that 18 volt, and my peak to peak, which is the ripples of the output, is 29 millivolt. Okay, so we are still in our margin for the voltage ripple, and we get to put the to boost the voltage from 12 to 18. Okay, for the boost part, as you can see, I changed the schematic, general schematic. Since the second switch should be off all the time, I just removed it, and no fall, no. Okay, for the boost schematic, as you can see, I removed the second switch because it should be always off. So doesn't matter if we remove it in the simulation. I connected the PWM to the gate of the first switch, and I want to try to see if I would get the 5 volt voltage at the output based on the duty ratio and everything that we set. Now let's try to simulate that. I hit run, and okay, that's actually very good. I reached the 5 volt, okay, and my ripples are around one, or like let's say 2 millivolts. So it's very good kind of like output that we could get is actually okay. Now the simulation is finalized, is 1.38 millivolt of ripples, and exactly 5 volt. That's very kind of like good, and is very kind of like idealic kind of situation. But our boost circuit also works. So basically this is this results in the simulation actually give us a very good confidence, that the design that we made is actually working. I already built the circuit for the Bach circuit, okay? Put down all the elements based on our design. I'm applying it to a volt DC as my reference source, okay? And I'm using the function generator to create the pulses, the PWM that I need to trigger the MOSFET, and using the oscilloscope to see what is the output voltage, which is the voltage across the load. Now, as you can see, the output that I have here, okay, is 1 unit. It is the amplitude is 1 unit of the grids that I have here, and my volt division is 5 volts. So I am getting very nearly perfect voltage of 5 volt. Now the actual average of these, I hope you can see there is a ripple. The actual average of this voltage, which is near the 5 volt, is 4.35. Okay, so it's not exactly 5 volt, and I expected that because my components are not ideal, but I am very close to what I intended, and the overshoots or the ripples that I have, the maximum voltage of the ripple that I have is voltage peak. I wanted to emphasize that it is not the whole ripple. What we discussed about the ripple and identifies as a quantity for the ripples is peak to peak, not the peak. Okay, this is peak that I wanted to tell you. My peak voltage for the ripples is about 700 micro or 0.7 milli. Okay, which if you consider the peak to peak, it is gonna be 1.4 millivolt within what we discussed and what we targeted. Actually, is very good in the assignment. Okay, so this is how my Bach circuit actually worked in the lab. Okay, so far we talked about the theory behind the Bach boost converter, and we design one, we simulate both Bach and boost converter, we build the Bach converter in the lab and see that it's actually our design works perfectly. And you can also build, you can also build the boost converter out of your circuit. Now, there is a problem. Based on the inventory that we have, all the MOSFETs that we own in our lab and we have available in our lab, they all need a voltage between gate and source of around between 10 to 12 volt of gate source voltage in order to be in a state on that IV characteristic that we talked about, to be in a state that it actually can provide enough energy and current to boost the voltage. Now, we don't have such a luxury in our resources. All the signal generator that we have, which we use it for triggering the switches and basically using as a PWM generator, at best it would give us like 8 to 9 volts, so 0 to 8 to 9 volts. Okay, the nominal is 10, but it never gets to 10. So basically that means we are able to trigger the MOSFETs, but the level of the VGS, if you remember the IV characteristic of the MOSFET, we had different curves for different value of the VGS, and each curves would end up in a certain amount of saturation current, like in the linear part. Sorry, in the constant part, we had a level of current, and as we move up in a VGS, we would be able to provide more current. Okay, so at the level that we have, we cannot fully trigger our MOSFET in a state that can provide enough energy, i.e. current, for us, based on our load, to boost the voltage to 18 volt. Okay, the circuit that we designed works perfectly. The resources that we have would not make us able to like provide such a boost in our voltage. Okay, now you might think that, okay, we using the same signal generator and same MOSFET in our box circuit, how come that works but this one won't work? Now in box circuit we actually lower down the voltage, meaning the output voltage, for example, in our case 5 volt over the load that we have, 100 ohm load that we have, it would basically drain less current rather than the case that if we wanted to have like 18 volt at the output. It is very clear, it's Ohm's law. So it works in a buck because the level of energy and current that we needed for the buck was in a state, was in a margin in the IV characteristics that our signal generator or VGS would satisfy the limit, the targeted current that we need. But in boost, we cannot reach that level, okay, of the current in our RV characteristics. So based on that, neither me or you are able to like actually implement the boost circuit and test it successfully in the lab. If I could handle to get the parts that I ordered, the new model MOSFET that works with a lower voltage gate source in time, because we are running out of time. We are almost in the second week of the November. If I get that in time, I would repeat the test and record the video and upload it so you can actually see how it works in the lab. But for now, our design in our simulation works, so we are good to go. If we implement that circuit with a proper PWM generator, okay, with a little bit of error, still we would have the same result. So they're good for our design. We have limited resources, and this is the hard face of the, or the cruel face of the life. Okay, so that being said, we are basically finishing the video for the buck boost converter. And as I said, if I get the part in time, I will repeat the whole process using the new MOSFET and record that and give you and upload and post that video for you. But remember, if for your own, if you wanted to build a buck boost and you're using any MOSFET beside the BS170 that we have, like I used, then you need to repeat all the design, okay, from the beginning, because the capacity of the switching frequency of BS170 is quite low. That's why I used 5 kilohertz as a frequency. Okay, if you have a proper gate signal, you can even go up to 250 kilohertz. Okay, and basically because of the voltage level that we have and the characteristics of those signal that we have, we could have different. We would have different kind of like voltage and currents all around the circuit. So that means we need to redesign for like the inductor, for the capacitor at the output, and for the biasing resistors that we used for our switches. So that being said, we are finishing the video, and if you have any question still, please don't hesitate to contact me, and so we could make sure that everything is clear and to the point. Thank you.